Hi, my name is Junho,
I'm
and
Ivan.
we are going to present our project on pneumonia detection from chest X-rays using optimized CNN. Pneumonia is a respiratory disease where the air sacs inside the lungs become inflamed and filled with fluid or pus. Pneumonia is also a major global health problem, causing millions of deaths every year. The challenge is that pneumonia does not appear the same in every patient. Different infection and different patients produce different shapes in chest X-rays. Because of these challenges, there's a strong need for improved medical imaging analysis using deep learning. Previous studies already showed CNNs achieving high performance in detecting structures in medical images, such as in fetal, abdominal, and breast images. For our methodology, the CNN processes the X-ray through multiple convolution and pooling layers to extract features associated with pneumonia, and outputs whether the lungs are classified as a normal or pneumonia.
For the baseline, it has one convolution layer and one dense layer. The data is split between 70% training, 15% validation, 15 testing. From the baseline, you can tell that it does all right based on the accuracies and the losses, but there seems to be some overfitting because the training validation gap is rather wide. And based on the convolution matrix, you can see by the off diagonals that they're not the same color, meaning that the baseline is not properly categorizing the predicted with the actual true values.
For the early custom model version 1, we introduced L2 regularization to reduce overfitting, increase the convolution depth, and reduce the training epochs because the baseline model already reached peak validation performance early. We also used larger kernels in the earlier layers to capture broader opacity regions. The accuracy curves show that the training and validation curves stayed closer together compared to the baseline model, suggesting slightly improved generalization and reduced overfitting, but mainly because of lowering train accuracy. The loss curves show the more stable validation loss throughout training, but both the training and validation losses were still higher than the baseline model. For early custom model version 2, we decreased kernel size and increased number of filters. The smaller kernels allow the CNN to detect the final local opacity patterns, while the larger number of filters enable the network to learn a wider variety of image features. Although some fluctuations were still present, the accuracy curves showed a much stronger improvement compared to both the baseline and version 1 models. The loss curves also improved significantly, while there was still mild overfitting shown by temporary increases in validation loss. The model was able to recover and continue improving later in training.
The final custom model uses everything that worked on the previous models and puts it into one. The final custom model has the highest accuracies and highest loss or like the best losses. And the accuracy curves and the loss curves also are converging a lot better than all the previous models. And the gap decreases for the training validation gap. And also you can see that based on this graph that the final model does a lot better than all the other models in accuracy and losses. And in the confusion matrix, you can also see that the off diagonals are about the same color, which is meaning that there's very low likelihood that it's choosing incorrectly. And you can see based on the X-rays that it's mostly blurry images that is causing the problem. As a takeaway, you should always evaluate the models based on many matrices, like in the V1 higher loss, as well as the resources taken by V2. And the CNN should always work as a decision tool support and never as an actual final answer.